Hello everyone, welcome back to our episode 6 of the number series. Today we're gonna talk about the problems on chapter 6 about the the modulus of some of the exponent numbers. Okay, and we learn about what is the Fermat theorem. So let's jump right in. So the first one is a very typical example that 5 and 7, they don't share any factors, and 7 minus 1 equal to 6, then this is equal to 1. And based on that, we times 25, we get 5 to the power of 8, have a remainder of 4. And for this one, after we simplify this by taking the remainder of 7, this number over here, 1945, we get 6. And using our Fermat theorem, we get 6 to the power of 6 is equals to 1. And 6 and we times 6 squared, and we have a remainder of 1. And similarly, we just do the same thing and just check your work for the question number 2. And question number 3. So when I try to do those kind of problems, when you have to find the modulus of those very big exponent, I try to find some special numbers in which it's equal to 1. And then we try to take the remainder power and we multiply that, and we get the final result. That's the strategy. And let's just take those two as an example. Okay? And yeah, I think it's just a little time consuming process to do those problems, but I think eventually you're gonna get the solution in one way or another. It doesn't matter. So let's see, 5 and 6, not much difference. This one is just a Fermat theorem, very straightforward. And this one, another technique is that if you see a number like this, the base is 1 less to the modulus, you can rewrite it like form like this, and it is equal to negative 1 to this to the power, and it's equal to 1 if this is even, odd if this is, or if it's odd, it's going to be negative. And question number 7, what is the remainder when this big number divided by 165? We're gonna make a note that 165 is not a prime, so but soon you're gonna find still there's a very interesting number here, and we can make it negative 1 and to the power of 32, 1, and we got this number left, and we take the remainder and we got 31. And question number 8, what is the remainder of 2001 to the power of 2001 when divided by 26? Yeah, this is the one where the base is 1 less to the modulus, and we apply this technique, we get negative 1. And question number 9, show that this equals to negative 1 to the power of r times r factorial. So we can rewrite this due to the congruence relationship. We get rid of all those p, and we get negative 1, negative 2, all the way to the negative r, and that's equals to negative 1 to the power of r times r to the factorial, which is what we are trying to prove. And question number 10. Calculate n minus 1 factorial modern for n equals to those numbers. Well, you're gonna find that within those factorials, there's all the factor for those numbers. It should be always equal to 0 as the number here is divisible by this. And how to prove it is that, assuming if n can be rewritten as some form of a times b, where a be a different number, we can know that a is less than n and b is less than n, and we're gonna assume that a and b, they are not equals to 1. And their factor must be somewhere in the form of this factorial. If n can be rewritten as a times another a, and we know that there's a total of a minus 1 multiple of a over there, because of n equals to a times a, and we have the section where the number inside is greater than 0 times a and 1 times a, and the section greater than 1 times a but less than 2 times a, and the n goes all the way up, and it includes all of the numbers that's greater than 0 times a but less than a times a. And that's how we know there's a minus 1 multiple of a, and we just need to make sure n minus a is greater or equal to 2. And yeah, n is greater or equals to 3. And question 11 show that 2 times p minus 3 factorial plus 1 is congruent to 0 modulo p. So this is the traditional Wilson theorem statement, and we take out of p minus 2, p minus 1, and we can, due to the congruence, we kick off the p, and if we take this negative 1 from this side to this side, we get a result that is desired. Okay, question 12. So Euler, he said that I derived certain results from the elegance theorem, and a to the power of n minus b to the power of n is divisible by the prime n plus 1 if neither nor a and b is, and prove this theorem use the Fermat theorem. We know that by Fermat theorem, n plus 1 and ab, they don't share any factor, that's why we get those two, and therefore, since those two numbers, they are both congruent to 1 modulo n plus 1, therefore they must be divisible by n plus 1, congruent to 0. This one should be very easy, I suppose. Okay. Question 13. We notice this little pattern here and try this decision for modulo 11. Well, for the time issue, I'm just not going to do too much. And these are the first few. And how do we prove it? Is that by using induction, suppose this is right and a is some number either equals to 1 or negative 1. And we take out the biggest factor from this factorial out, and then we use the congruence and knock out the p over here, and we reverse it to positive, so the both sides is going to multiply by negative 1, and we get the next expression for this little sequence here, and we reverse the value of a, which is the desired result that we want. And question 15. we need to show that if P is an odd prime, we need to show this. This ugly expression is it's congruent to -1 modulo P. So we know that by the Fermat theorem, since those numbers, they're smaller than a prime number, which means they cannot be a multiple of P. The only way that a number can share some kind of factor with a prime is that it is the multiple of that prime. Since they are all smaller, that's impossible. And by the Fermat theorem, we have a total of P minus 1 of 1s adding together, and we get P minus 1. The modulo is equals to -1. And for B, we're using the similar results that we got from A, and except we multiply 1, 2, 3, those numbers at the front of each one of the expressions, and we got this. Since P is a prime and P minus 1 is even, and this must be an integer, so this whole thing is going to be a multiple of P. That's why it is congruent to P. It is divisible by P. Next question. Show that the converse of Fermat theorem is false. So we notice that 341 is a composite number. It is 11 times 31. And we calculated, find that the remainder is equal to 128. Question 17. So we need to prove that PQ is a divisor of these. Let me to focus it so that you can actually see. Okay, it's slightly better. So this expression should be a multiple of PQ. And we can try to factor this, and we take out the A squared. And use the Fermat theorem. Those two numbers should be this expression is a multiple of P. This expression is a multiple of Q. And together this whole thing should be a multiple of PQ. So let's take a look at question B. So this expression, we still need to prove that it is a multiple of PQ. Let's suppose we just focusing on the factor of Q. How do we gonna prove that? Is that we first take out of a factor of A, and then for those two numbers, we take out the factor of A to the power of P minus 1, and we got this. And for those two, we just put it aside, and we analyze those two individually. We will find that each one of them, they are actually divisible they are multiple of Q by the Fermat theorem. And similarly, since we can see that PQ, they are actually interchangeable, right? The same result we should get for modulo P. And since PQ, they are different prime factor of this whole thing, that means PQ must be divisible by this whole thing. Because they are different, they are not sharing any common factor. And question 18 show that 2p is a divisor of 2 to the power of 2p minus 1 minus 2. So this one should be easy. You just take out the factor of 2, and this thing by the Fermat theorem, you should find out that it is indeed a multiple of p. And question 19. For what value of n it is true p is a divisor of this thing here? So we're gonna note that in order for that conclusion to be true, n and p, they don't share any factor than 1. n minus 1 and p, they don't share any factor than 1. They must be both satisfied in order for the conclusion to be true. We're gonna find that if those two conditions are satisfied, then those things are actually a permutation of 1, 2, 3 all the way up to p minus 1. And we got this conclusion. And this is indeed a multiple of p. If n and p, they do share some kind of factor, then we know that those different things, they should be... No, I don't think there is a value for a solution in which n to the power of k is congruent to 1, which means this is not a permutation from 1 to p minus 1. It's more like 2, 4, 6, like depending on the factor it's sharing. It's d, 2d, 3d, all the way up to, I don't know, I think it's, yeah, I think it's p minus 1d all the way up to that, and that's why it's going to be false. Oh, wait, hold on. Oh, never mind. So this p is a prime factor. That means if they share some kind of factor, n is a multiple of p, and it's going to be 1 plus 0, 0, 0, 0, 0, and the remainder is equals to 1. It's not equals to 0. And if n minus 1 and the p, they don't share, if they do share some kind of factor, that means, okay, I think that's a little confusing because I think I should erase it. Okay, let's here. If they do share some kind of factor here, then we can rewrite this as a plus 1 plus 1 plus 1, this p minus 1 plus 1s. So the modulus is equal to negative 1. And I think, okay, let's explain that way. So if they do share some kind of factor, we can say for certain that n could be expressed, n minus 1 could be expressed like this, and n is kp plus 1. And since we are talking about the modulo p here, so we don't care about this. And all of the n, the base is going to be 1. It doesn't matter the power, they're gonna become 1. And that's why there are so many 1s here. And the result is going to be negative 1. Okay, I hope that addressed your confusion for the problem. And let's take a look at question 20. Show that for every odd prime except 5, it divides some number of 4 more like this. We suppose 10 to the power of k, and the p is not equal to 2 and 5. We know for certain that 10 and the p, they don't share any factor, since other primes could not have the factor of 2 and 5. And let's discuss a very special case in which p equals to 3. If p equals to 3, then this thing is going to always have then all of the 10 to the power of k, they have a remainder of 1. And this is kind of special. And we find an example that 1, 1, 1 is divisible by this. And otherwise, it's going to be this 10 to the power of k, the remainder is going to be a permutation of this. And that's why we can conclude that if we sum them together, it's going to be p minus 1 over 2 times p, which is the divisor of p. And we can rewrite those sum of 10 to the power of k to the actual an extra number, and there are a total of p minus 1 digits of 1, which is divisible by the p. And that's all for today, and thank you for watching this video. I know it's quite long, and thank you for your support. Goodbye.